Hello! I figured while I was learning about primitive recursive functions, I might as well do some research into primitive recursive arithmetic and talk about that as well. And I was not disappointed. As we saw in previous videos, we can work with equalities and Boolean logic using primitive recursive functions, and this actually allows us to develop an entire logic, a tool for proving facts about natural number arithmetic. It's not the most powerful logical tool. There are things that it can't prove, and in fact, things it can't even express. But that's actually a good thing. It's a nice backup logic in case we accidentally prove that the stronger systems we more commonly use are inconsistent. Primitive recursive arithmetic was created by Skolem in the early 1900s. Around this time, mathematicians were responding to Russell's paradox. The ways they used to reason about sets were inherently contradictory, and so there was a scramble to try to establish a solid foundation for the various branches of math, to make sure there weren't any other branches of math with fundamental contradictions. And that's not an unreasonable thing to have feared. Analysis had been, up until the recent work of Weierstrass and others, plagued by paradoxes, for instance, those of infinite sums that mathematicians amuse themselves with to this day. Just as there was well-deserved wariness around infinite sums and products, there was a wariness of the quantifiers for all and there exists, since these are just infinite ands and infinite ors. Saying there exists a prime number is the same as saying 0 is prime, or 1 is prime, or 2 is prime, and so on and so forth. An oring together of infinitely many statements. Saying every number satisfies P is the same as saying 0 satisfies P, and 1 satisfies P, and 2 satisfies P, and so on and so forth. An anding together of infinitely many statements. And so if we could get ourselves into trouble with infinite sums and infinite products, maybe we can also get ourselves into trouble with infinite ands and infinite ors. And so Skolem creates primitive recursive arithmetic with the ability to prove a bunch of basic facts about arithmetic, but with no infinite ands or infinite ors, hence a finitary system of reasoning. He introduces it as, if we consider the general theorems of arithmetic to be functional assertions and take the recursive mode of thought as a basis, then that science can be founded in a rigorous way without use of Russell and Whitehead's notions, always and sometimes. I'm actually going to present primitive recursive arithmetic based on Goodstein's Recursive Number Theory from 1957, since this presentation takes advantage of the fact that we can already talk about Boolean logic using primitive recursive functions. So we don't need anything but equalities involving primitive recursive functions in our logical system. It's an incredibly simple system, but Goodstein is able to use it to state and prove versions of unique prime factorization and the Chinese remainder theorem. I really had fun reading the opening few chapters of Goodstein's book, so I'm just going to quote Goodstein. A proof is a table of equations, each of which is one of part of the definition of a function. Goodstein lets us define functions in two ways, either using primitive recursion or as a composition of previously defined functions. So this can either be the base case or recursive case of a primitive recursive definition, or just the definition of a function as a composition. I'll use the all caps word definition to indicate that a line is of this form. An equation of the form f equals f, I'll use the word identity to indicate that a line is of this form, or is a proved equation. There are three ways to generate new equations in this system. First, if f equals g is a previous equation, then we can replace f by g in another previous equation. This is one of the basic algebraic substitutions. For instance, because we know that x squared equals x times x, we can freely replace any instances of x squared by x times x in a formula. In this case, a previously proved equation. I'll use the term equality replacement for this kind of substitution, although it's sometimes called other names like the principle of substitutivity or the indiscernibility of identicals. Furthermore, since we're going to be proving equations that are true for all x, like x squared equals x times x, we can replace all of the x's in these sorts of equations by whatever we want, provided we replace the variable at all the points at which it occurs, and we replace it by a thing of the appropriate type. I'll call this universal replacement. Sometimes this is called universal instantiation. Finally, Goodstein gives us a bit of induction. We can conclude f equals g if f and g both satisfy the same recursive definition. Goodstein calls this the uniqueness rule. Let's go through a very basic example from Goodstein, proving that 0 plus x equals x by the uniqueness rule. In order to do this, we need to verify that the left and right-hand sides of our equation, f of x equals 0 plus x and g of x equals x, respectively, both satisfy some definition of some function h by primitive recursion. In particular, we need to show that we can plug f and g in for h into a definition that looks like h of 0 equals something and h of the successor of x equals something. Specifically, I'm going to show that f and g of 0 are both 0, and f and g of the successor of x are just the successor of f and g of x. If we plug in f of x equals 0 plus x for h into both of these equations, we specifically need to show that 0 plus 0 equals 0, and 0 plus the successor of x equals the successor of 0 plus x. It'll take a few steps to show these with only the proof steps that were allowed. If we plug in g of x equals x for h into both of our equations, we need to show that 0 equals 0 and the successor of x is equal to the successor of x. These are both just identities. Just so that we're all on the same page, here's the primitive recursive definition of addition that we're going to be working from. Whenever you're proving something about a primitive recursive function, it's always important to have its definition ready to reference. So our formal proof is going to be a series of lines. Each line is an equality with very precise rules about how we can get from one line to the next. Let's start with x plus 0 equals x. We're allowed to write this down since this is the first line of our definition of addition. Next, if we replace all the x's with zeros, we get 0 plus 0 equals 0, one of the things we were trying to show, and this holds by universal replacement applied to line 1. Next, we go back to the definition of addition. The second line says that x plus the successor of y equals the successor of x plus y, so we can write that down. If we then replace all the x's with zeros and all the y's with x's, we get 0 plus the successor of x equals the successor of 0 plus x, the second thing we were trying to show. The third thing that we needed to show was that 0 equals 0, which is just an identity. And the fourth thing we needed to show was that the successor of x is equal to the successor of x, which is also just an identity. Note that you really only need one identity, x equals x, and then you could use universal replacement to replace those x's by whatever you needed, but that's an annoying extra step. So now we've shown everything we need to apply Goodstein's uniqueness rule to lines 2, 4, 5, and 6, giving us that 0 plus x is equal to x. So this is great. We have a formal system of reasoning about arithmetic with, just 5 different rules for how to get from one line to the next. Let's do another example, again from Goodstein, just because it takes some practice to get used to working with the uniqueness rule. Suppose we wanted to prove that addition was commutative. Again, we set up functions f and g representing the left and right-hand side of the equation that we're trying to prove. And then we have to come up with some sort of recursive definition that we can prove that both of them satisfy. Let's go with the function applied to x and 0 gives us x, and the function applied to x and the successor of y is the successor of the function applied to x and y. If we plug f into the first equation, we get x plus 0 equals x, which is part of the definition of addition. If we plug f into the second equation, we get x plus the successor of y equals the successor of x plus y. which is the other part of the definition of addition. So both of these hold very straightforwardly. If we plug g into the first equation, we get 0 plus x equals x, which is what we showed on the previous slide. So we can just copy the lines of that proof into our proof of commutativity. And if we plug g into the second equation, we get that the successor of y plus x is equal to the successor of y plus x, which we'll show on the next slide. And so once we've constructed a proof that shows all of these four different things, we can apply the uniqueness rule to conclude that x plus y is equal to y plus x. So again, we're going to show that the successor of x plus y is equal to the successor of x plus y, and we'll prove this again using the uniqueness rule. To show that these two expressions are equivalent, we'll show that both of them satisfy the recurrence. H of x0 is the successor of x, and h of x, the successor of y, is the successor of h of x and y. Plugging the left-hand side in for h, this requires showing that the successor of x plus 0 is equal to the successor of x, and the successor of x plus the successor of y is equal to the successor of x plus y. And plugging the right-hand side in for h, this requires showing that the successor of x plus 0 is equal to the successor of x, and the successor of x plus the successor of y is equal to the successor of x plus y. So again, we need to show all four of these different things in order to be able to conclude the equation that we want by the uniqueness rule. Showing that the successor of x plus 0 is equal to the successor of x is easy. This is just the base case definition of addition, x plus 0 equals x, with the x's replaced by successor of x's. Showing that the successor of x plus 0 is equal to the successor of x is also easy. This is just the identity, the successor of x is equal to the successor of x, with one of the x's replaced by x plus 0, which we know is equal to x from line 1. So here we're applying our equality replacement rule, that if two things are equal to each other, we can replace one by the other and get a new true equality. Showing that the successor of x plus the successor of y is equal to the successor of x plus y requires us to look at the inductive case definition of addition and replace all of the x's with successor of x's. And finally, we can show that the successor of x plus the successor of y is the successor of x plus y by just taking the inductive case definition of addition and taking the successor of both sides. So the uniqueness rule applied to lines 2, 4, 6, and 8 with this particular inductive definition of h allows us to prove the desired equality. And we can prove all of the basic properties of all of the primitive recursive functions that we could want similarly. For fun, you might want to try proving associativity of addition and distributivity. These are straightforward applications of the uniqueness rule and the definitions of addition and multiplication. But the goal of primitive recursive arithmetic is to not just capture universal equations. We also want to be able to capture some amount of first-order logic, so we can express more complicated mathematical statements. It'll be important to note that all of the variables in our equations are being implicitly universally quantified over. When we prove that x plus y is equal to y plus x, we're saying that this is true for all x and for all y. One might argue here that we've already lost our way. Remember that the goal of primitive recursive arithmetic was to avoid quantifiers over infinite domains. Perhaps, but at least our quantifiers cannot get into too much trouble if they're all of the same kind and all at the beginning of our formulas. Recall from previous videos that if we use the number 0 for falsehood and 1 for truth, we have primitive recursive functions like isEqual that takes in two inputs and returns a 1 if they're equal to each other and a 0 otherwise. Or isLess or equal that allows us to compare two inputs. Goodstein actually uses 1 for falsehood and 0 for truth, since this makes the is-equal function easier to express, but I'll stick with the more modern convention for this video just so that it isn't confusing. We can also express Boolean operations, such as or, and not, acting on our Booleans 0 and 1, and since these are primitive recursive functions, we can use them in our primitive recursive arithmetic. For instance, we can express the universal fact that x is less than or equal to y, or y is less than or equal to x, by taking the Boolean output of is less or equal and feeding it into our or function, and then expressing that the result is identically 1. This gives us an equality of expressions involving primitive recursive functions, and we can prove it in primitive recursive arithmetic. Going back to Skolem's original article on primitive recursive arithmetic, a logical foundation can be provided for arithmetic without the use of apparent logical variables. Here, Skolem is using the term apparent variable to mean a bound variable, that is, the variable of some quantifier. This was the term used in Russell and Whitehead's Principia Mathematica, to which Skolem's article is a response. To be sure, it will often be advantageous to introduce apparent variables, but we shall require that these variables range over only finite domains, and by means of recursive definitions, we shall then always be able to avoid the use of such variables. So let's do just that, extending from only being allowed universal quantifiers outside our formulas to also allowing bounded quantifiers inside our formulas. Given a primitive recursive function f of x, we can define a new primitive recursive function, sigma sub f, with sigma sub f of 0 being equal to f of 0, and sigma sub f of the successor of x equaling sigma sub f of x plus f of the successor of x. As such, sigma sub f gives us the partial sums of f. Specifically, sigma sub f of n is the sum of f of 0 through f of n inclusive. And we can define the partial products of a function f using primitive recursion in the same way. The product of the first value is just f of 0, and the product of the first x plus 1 values is just the product of the first x values times the next value, f of x plus 1. And then we just note that multiplication and addition kind of correspond to logical and or respectively. If p of x is some sort of Boolean valued function, let's say that it's an assertion that 2 times x equals x times 2, then the product of the values of p from 0 to y is going to be 0 if any of those values is 0, and 1 if all of those values is 1. In other words, this product is 1 if for every x less than or equal to y, p of x holds. So as promised, we have bounded quantifiers, quantifiers where the variables range over only finite domains. Now, of course, this isn't interesting on its own. We could already express and prove that 2 times x was x times 2 as just a basic equation, or by saying that is equal of 2 times x and x times 2 was equal to 1. But the key thing here is that it allows us bounded universal quantifiers deep inside of a formula, not just on the outside. So it's more than what we had before. Similarly, the sum of p of 0 through p of y, it's going to be at least 1 if p returns true for any of the values between 0 and y. So if we add an is non-zero function outside, so we actually output a Boolean, it's the same as saying there exists an x less than or equal to y such that p of x. So now we can express bounded existential quantifiers as well. And so it is as Skolem says, we can make use of quantifiers, and it will be useful to do so, but we'll require that our bounded variables come from finite domains, namely the numbers x less than or equal to some y. And we can always get rid of these quantifiers and variables by making use instead of the recursively defined sigma and pi sub f functions. Let's do an example. Suppose that we wanted to create a primitive recursive function that told us if a number was prime. That is, it returns a 1 if its input is prime and 0 otherwise. Of course, this predicate has to be primitive recursive since it can be computed in a reasonable amount of time. see video 2 in this series. And you could probably come up with some sort of tricky way of doing this directly, but let's practice translating expressions with bounded quantifiers into primitive recursive notation. So let's start by expressing our isPrime predicate using bounded quantifiers. A number z is prime if for every number y less than or equal to z, either y is 0, 1, or z, or y does not divide z. That is, there's no x less than z with x times y equal to z. In order to express this, we're going to need to define sigma sub f and pi sub f when there are other variables involved. We don't do anything with those other variables, they just come along for the ride. As one might expect, we're going to work through our formula from inside out. So first we're going to define a primitive recursive function, f of x, y, and z, that tells us if x times y is equal to z. Then sigma sub f of w, y, and z tells us if there is an x less than or equal to w, making x times y equal to z. So sigma sub f of z, y, z tells us if there is an x less than or equal to z, making x times y equal to z. In other words, it tells us if y divides z. Using our Boolean operations, we can do a multivariable composition to produce a primitive recursive function g of yz that tells us that y is 0, 1, or z, or does not divide z. That is, y is not a factor that witnesses that z is composite. So pi sub g of wz expresses that for every y up to w, y does not witness that z is composite. And so pi sub g of zz expresses that none of the numbers all the way up to z are factors that witness that z is composite. Don't forget, of course, that everything in primitive recursive arithmetic is an equality. So if we wanted to say that a particular number p was prime, we'd have to say that pi sub g of pp was equal to 1. And of course, we can use our quantifiers not just to create primitive recursive functions, but to make logical statements about arithmetic, such as the infinitude of primes. One way of expressing the infinitude of primes, at least in first-order logic, is that for every x, there is a larger y, which is prime. But this isn't a formula of primitive recursive arithmetic. The universal quantifier out front is fine. That's the default, as we've seen, for primitive recursive arithmetic, but the existential quantifier is no good. The range of possible values of y that we're quantifying over is infinite, and that's not allowed. The only sorts of existential quantifiers that we can have are bounded existential quantifiers. So instead, in primitive recursive arithmetic, we have to say something like, for every x, there exists a y less than or equal to x factorial plus 1, which is larger than x and is prime. This is specifically what you get when you look at Euclid's proof of the infinitude of primes, and Goodstein provides a full proof of this fact in primitive recursive arithmetic. So something that you could translate into a full tabular proof of this fact here. Indeed, the limits of primitive recursive arithmetic are often not in what you can prove, but what you can even express. For instance, we can't prove anything about the Ackermann function, but that's because we can't even express the Ackermann function. One can imagine trying to reason about a set that's not quite as nice as the primes. For instance, Heijenoort, in an introduction to Skolem's paper, gives the example of the twin primes. If we knew more, maybe we could express that there were infinitely many twin primes, using a similar sort of construction to what we have here. But maybe we couldn't if the twin primes grow too far apart too fast. But because we don't know anything, we can't even come up with a single formula to ask if that formula is true or false. Even to state that there are infinitely many twin primes requires some knowledge about their growth. Goodstein provides an explicit construction of a primitive recursive function to determine if a number x encodes a valid proof in primitive recursive arithmetic. That's one of the joys of formal systems of proof. One can write a computer program to check if a proof is correct. And since such a program runs in a reasonable amount of time, the function that it calculates must be primitive recursive. But this is also one of the perils of formal systems of proof, because now we can create an equation in the language of primitive recursive arithmetic that expresses, for every m does not encode a proof of this statement itself. With a little bit of thought, you can see that such a statement must be true, but unprovable in primitive recursive arithmetic. So there are statements that primitive recursive arithmetic can express, but not prove. This is a standard Gödel's incompleteness theorem proof, and again, all the gory details are in Goodstein's book. But such an example is terribly artificial. In 1999, Harvey Friedman conjectured that every theorem published in the Annals of Mathematics, whose statement involves only finitary mathematical objects, can be proved not just in primitive recursive arithmetic, but actually a restricted version of primitive recursive arithmetic called elementary function arithmetic, where we're restricted to addition, multiplication, and exponentiation, and ignore the higher hyperoperations. And this is really just a fancy way of saying that we aren't likely to encounter statements that can be expressed but not proved in primitive recursive arithmetic in everyday mathematical research. And there are various theorems that suggest that this might actually be true. For instance, there's a result that in order to prove a statement that we can express but not prove in primitive recursive arithmetic, we need to make use of a system more powerful than WKL0, a logic that allows us to prove a wide variety of important mathematical results, including the extreme value theorem and Gödel's completeness theorem. Recall that primitive recursive arithmetic came about in a time of foundational crisis for mathematics. Hilbert had hoped that by formalizing mathematics, by replacing the natural language arguments, the proofs that we're, as mathematicians, more familiar to seeing, by replacing those with pure line-by-line computerized proofs in some particular formal system, such as the one that we've seen for primitive recursive arithmetic, and then proving that formal system to be consistent, it would be possible to ensure that what remained of mathematics after Russell's paradox did not also have nasty surprise contradictions for us. As Hilbert says, we must establish throughout mathematics the same certitude for our deductions as exists in ordinary elementary number theory, which no one doubts and where contradictions and paradoxes arise only through our own carelessness. But what would that proof of consistency look like? It couldn't use any suspect proof techniques of its own if we wanted to be sure of the results. Would we be happy with a proof in words, like the natural language sort of arguments that we're used to making in mathematics? Or would this proof of consistency itself have to take place in some formal system? Let's take a look at a proof that primitive recursive arithmetic is consistent. And again, this is from Goodstein. This shows up various other places as well. We say that an equation is verifiable if when we plug in numbers for the variables in the equation, we get the same numbers on both sides. This is a fancy way of saying that our equation is true. X plus y equals y plus x is a true equation because when we plug in whatever numbers we want for x and y, we always get equal numbers on both sides. And then we just prove by induction, on the length of our proofs, that every equation we can prove in primitive recursive arithmetic is verifiable. So we can't, for instance, prove that 0 equals 1, which we could if primitive recursive arithmetic was inconsistent. So I want you to actually take a moment here and think about how compelling this proof actually is. Does this convince you that primitive recursive arithmetic is consistent? Well, it feels a lot like this example of a proof given by Kreisel of the sort of consistency proof that Hilbert was explicitly not looking for arithmetic. When read in the intended manner, the axioms of, for instance, Zermelo's set theory are true of the concept of set, and the rules of proof are such that true statements are transformed into true ones. Hence, the formal system is consistent. Again, some sort of inductive argument. This sort of proof initially looks compelling, but if somebody proposed an axiomatization for pre-Russell set theory before Russell's paradox was published, this proof would appear to apply just as well to that. So it would prove, it would quote-unquote prove the consistency of a system that was inconsistent. Now, there's something a little more clever going on here in our consistency proof for primitive recursive arithmetic. We can define, purely in terms of symbolic manipulation rules, what it means to plug numbers into a formula in primitive recursive arithmetic. What it means to plug numbers into a multivariable composition, what it means to unwind a definition by primitive recursion to calculate a primitive recursive function on a particular input. So there's a sense in which if something goes wrong with this proof, then something has really gone wrong with the notions of symbolic manipulation themselves, our intuition for the rules for manipulating logical expressions. But it's been argued by Poincaré, for instance, that this proof is trying to justify that it's safe to use induction in the form of the uniqueness rule in primitive recursive arithmetic by appealing to induction on formulas. And so we haven't really learned anything about whether induction is safe to use or not. In fact, it requires a stronger formal system than primitive recursive arithmetic in order to prove the consistency of primitive recursive arithmetic. It uses kind of a stronger sense of induction than what we have just by the uniqueness rule. But anyway, primitive recursive arithmetic, because of its simplicity in terms of assumptions and its power to express most of everyday finite mathematics, plays a prominent role in many discussions of the foundation and philosophy of mathematics. So thanks for watching, and thanks for following along with Primitive Recursive March. I'm still learning about primitive recursion and primitive recursive arithmetic, so if you know more about them, please share what you know below. Please also leave any questions or comments you might have as well, and be kind to each other.